My name is Dr. Melara in the math department, and this presentation is being done with Dr. Barnaby, and I'll let her introduce herself too.
I'm Dr. Barnaby. I'm also from the math department.
And so thank you again for joining us. We're very happy to share what we have, the role of mathematics plays in what's going on right now. So we titled this presentation, The Role of Mathematics in Flattening the Curve. And can we move on to the next slide?
Yep, there we go.
So one of our goals is to show you give you an insight into some of the mathematical methods in that are being used at the moment. And a lot of these methods serve as a foundation and inspiration for what's going on. Last week, the president of the Society for Mathematical Biology, which is the largest professional organization for mathematical biology in the world, Professor Alexander Anderson, he sent a message to the society members, and we took this excerpt from his message. So this reads, "The predictive mathematical models that capture the underlying mechanistic biology of specific processes are at the heart of everything we do. The COVID-19 virus pandemic has brought into sharp focus the critical importance of mathematical models in both making predictions about current trends in the disease dynamics, but also how specific interventions such as social distancing might modify them. Understanding these interventions theoretically becomes important not only for mathematical biologists, but also for politicians and other decision makers." So the way that we're going to approach this presentation, we're going to introduce you to a simple mathematical model. In fact, it's going to involve a lot of arithmetic operations only. And from there, we're going to generate this curve that we keep on seeing on the news nowadays. And then we're going to build onto a calculus-based model from there. And we have used real world data, like current data, that is being published publicly. And we're going to show you how the mathematics from those models compares to the actual data that's being published and collected. So next slide, please. So to describe how this process works, I'm going to consider a very generic scenario. I chose 10 randomly selected individuals, and then I'm going to suppose that this is a Monday, for example. And the first thing I'm going to do is I'm going to call this first day Monday. I'm going to label it day 0. And the next slide. So I need to keep track of the number of individuals in day 0. So at the moment, there are no individuals that have any disease. And then suddenly a new individual jumps in, and this person has a disease. So then now we have 11 members in this community, and I'm going to also keep track of this individual who is infected. Now, the individuals that are not sick, I'm going to call them susceptible because they can catch this disease from the infected individual, which is labeled with the letter I, and the susceptible individuals, I'm going to use the letter S to label them. So these are just numbers. And another thing that I want you to notice is that the argument or the input for both the S and the I functions, it corresponds to the fact that we're at day 0. So at day 0, we have 10 individuals who are not sick or they are susceptible to catching this disease. And we have 1 infected individual at the same time. So next comes Tuesday. So then we have move on to the next day, which is 1 day away from the original day. And there's lots of things that can happen on this day. So among them, it's possible that the disease is not transmitted. So then the number of individuals on day 1 will remain the same as the number of individuals from day 0. So I'm going to express that using mathematical notation as S of 1 is equal to S of 0, right? The number of individuals at day 1 is the number 1, and then the S for the susceptible individuals. I also keep track of the number of infected individuals. And since this person has not transmitted this disease, so then the total number of infected individuals in this community also remains equal to what it was on day 0. However, it's possible that this infected individual begins to infect others in the community. So you can see at the very top, outlined in a red, thick outline, red color outline, one of the members from this community was infected, and we don't know what this disease is like. It's possible that this person can only infect 1 individual on day 1, or maybe they can infect 2 individuals, or perhaps they could infect 4 individuals at day 1. But currently, if this were to happen, then the total number of susceptible individuals be reduced. So then, to express that mathematically, we're going to have to subtract from the original number of individuals on day 0, the total number of individuals that were infected. Now, we need to find a way that represents what it means to transmit a disease from one individual to another. So we do that in mathematical biology by using multiplication, which is why you see that S of 0 times I of 0. And then we have this weird Greek letter that looks like a B, so we call that a beta, and that contains information about the rate of infection. So depending on the values of beta, we could possibly infect 4 individuals on Tuesday or just 1 individual, so that it varies, and that value is usually obtained from data if the data is available to us. Now, so we subtract that amount of individuals who were susceptible. So since they are no longer susceptible, then they now move on to the different class of individuals who are infected. And that's where you see this same quantity being added to that equation at the very bottom. So we can express this scenario using symbols in mathematics, and especially in mathematical biology, we construct what are called flowcharts. So then the first compartment on the left represents the number of individuals that are susceptible. And then the one on the right is the number of individuals that are infected. And this process where individuals are infected and they move from the susceptible class to the infected class is denoted by that arrow pointing in that direction. And we normally write the rate of infection, or whatever rate of that occurred for this process to take place, right above that arrow. So then we can express this compartmental model using mathematical terms, and we have our first mathematical model. So this is a mathematical model that's commonly used in mathematical biology, and if you look at the inputs of the S and the I functions, instead of 0s and 1s, I've now replaced them with T's on the right-hand side of the equation, and on the left-hand side of the equation, I have a T plus 1, which is a generalization of what we had previously when we had 0s and 1s. You might remember that the quantities on the left had 1 less value in the argument than the ones on the right. Okay? So we can take this compartmental model or flowchart, and we can begin to consider many different scenarios. So for instance, we only considered the case where we have susceptible individuals that transmit this infection, so they move on to the infected class. But many things can happen. So among the things that can happen with infected individuals is that they can recover, okay? So then this is a very simple model, but then we can also talk about, well, what about susceptible individuals that died? And maybe they didn't die from the disease, they died from some other disease or a car accident, for instance. Or what about infected individuals that died from the disease? So you see those downward pointing arrows, and the same thing can happen for the recovered. That's what those arrows are telling us, that those individuals have passed away. Or We could also have the scenario where someone who has recovered from the disease returns to the susceptible class, so they're not immune to catching the disease again. And we can denote this by this arrow. And I think all of us, just by looking at this and considering all sorts of scenarios, we can begin to not just add more compartments and arrows. And I think it's wonderful that we can do that. But one of the things that we want to do in mathematical biology initially is just to begin with a very simple model and keep it as simple as possible to see if at the very best we can capture the dynamics, the primary dynamics that are taking place in this model. So what we're going to do is we're going to only keep the recovered class, and we're going to work with this model here that has a susceptible, infected, and recovered class. And right below that, we're going to write the equations that describe this compartmental model. Now, if you look at the first two equations, most of the terms match. There's a new Greek letter that was introduced between the infected and recovered classes that's called the gamma. So notice how that arrow is pointing from the infected compartment to the recovered compartment, and that explains that minus in front of the gamma times I. So that's a rate of recovery. And the third equation is only describing what's going on in the recovered class. So all those individuals that are leaving the infected class, the only assumption that we make is that they recover. So many things can happen, but again, remember, we're keeping this as simple as possible to work with a simple model. Yes.
Thing to note with this one, you can see that in this recovery term, it's just the minus gamma times I, which is different than the susceptibles moving to infected, because as we know, when we're sick and we get recovered, we don't need to come in contact with someone who's recovered in order to become better. We just, through some way, we get better. So that's why this term here doesn't have times R like the other transition one did.
Okay. So what this model is normally referred to is an SIR model. I think of it as some sort of branding, kind of like Kleenex refers to tissues. So when we talk about SIR models, we don't necessarily refer to this one model. There are many different kinds of SIR models. And later on, we're going to look at a different kind of SIR model that has different compartments that have been included